Okay, this is page 11, number 6. And it's another proof, so that's won't help you with it. The problem is we have a matrix and it has this property. If you square it, you get the matrix. There's a term for that. It's called eigenvalue. Take this condition, it's a particular matrix, and when you square it, you get it set back again. And then we want to show that every eigenvalue of this is either 0 or 1. So it seems a little abstract. How are you going to get there? I mean, all we have is this unknown matrix with this weird property, and somehow we're going to have to calculate the eigenvalues of an unknown matrix. So it seems like it's almost an impossible task. Let's recall how we find eigenvalues. To find lambda, to solve the determinant of l minus lambda I equals 0. That's what you solve in order to find lambda. Right? So, if this is 0, what does this mean? What does it mean for lambda to be 0? This right here means that we must have the determinant of a minus 0 I equals 0, right? Because this is what you have to solve to find lambda, and then if you got lambda to be 0, then you better have that. And similarly, if you had lambda equals 1, then you would have had to solve the determinant of a minus 1. So this is what happens. If you had lambda as 0, you would have determinant of a minus 0. If you had lambda as 1, you would have determinant of a minus I equals 0. Okay, so let's simplify this one. This is just determinant of a. Because there's a 0 here. So these are the two things that I want to have happen. Okay? So let's go and look now at this information here. Let's start with this. Okay? So let's start with a squared minus a. I don't know really where I'm headed with this. I just got to do something. Okay? I've got to start getting these determinants involved. And we'll head towards that in a second. The first thing I want to do is I want to set things equal to 0, because if you look over here, everything's equal to 0. So let's get everything equal to 0 over here. So that means we have a squared minus a equals 0. And then what's natural to do here? It's not as if you need to see where the proof is going. It's just you look at this and it's just sort of a natural thing to factor the a out. There are two terms, they both have an a in it. So let's factor it out. See where that leads. So a times a minus I equals 0. Look, that's promising because I have a minus I here. And I have it here. So what is it I need to get instead of a minus I? So now it seems very natural to take the determinant, because if I take the determinant, I'll get this kind of notation. I'll get the determinant of a, determinant of a minus I. So let's do that. This implies the determinant of a equals the determinant of 0. Okay, but the determinant of 0 is 0. That's the matrix with all zeros in it. So that's no problem. That's 0. So that gives us the determinant of a times a minus I equals 0. Okay, so all I've done is I left the left side alone, and I just realized that the determinant of 0 is just 0. And then I'm going to use my fact. We know that the determinant of AB is equal to the determinant of A times the determinant of B. That's a convenient fact for us. Because what that enables me to do is take the determinant here and here, and it's the same thing. So that implies that the determinant of A times the determinant of A minus I equals 0. So what happens when I have two numbers multiplied together and they equal 0? That means one of them is 0, right? You can't have 2 times something non-zero equals 0. So that means either determinant of A equals 0 or determinant of A minus I equals 0. One of them has to be 0 because the product is 0, right? Well, that means either lambda equals 0 or lambda equals 1, which is exactly what we wanted. You see, because if I had this, that means that lambda is 0. If I have this, that means that lambda is 1. So having that yields the result that we were interested in. So that's a proof. Now that's a little fancier, and I wouldn't expect you guys to even, to really be able to do that. Maybe a few of you could. But now that you've seen the proof, maybe you can learn to reproduce it yourself. So if you really want to learn how to do proofs, what you do is you take complete proofs that you know the complete solution to, and you start with a clean piece of paper, and until you can get from the top to the bottom without looking at the answer, then you don't know the proof. And it's sort of a combination of memorization and understanding the mathematical steps to do this. So this is a good one to practice with. Okay? So that's the complete solution.